The Constitution of India. Preamble. We, the people of India, having solemnly resolved to constitute India into a sovereign, socialist, secular, democratic republic and to secure to all its citizens justice, social, economic and political, liberty of thought, expression, belief, faith and worship, equality of status and of opportunity, and to promote among them all fraternity, assuring the dignity of the individual and the unity and integrity of the nation. In our Constituent Assembly, this 26th day of November 1949, do hereby adopt, enact and give to ourselves this Constitution.
Happy morning, students. I know you all are getting up early now because you have your improvement exam. Otherwise, we never see 6 or 7 o'clock, right? After this COVID has started, I know people have become very lazy by getting up at around 9:30, 10. It's not your fault, children, because you know there is nothing to do as of like I can watch my videos at my own comfort time. But children, you decide your own attitude, right? We decide our own character. So you are wholly responsible to get up early in the morning, at least before 7, do your regular schedule and try to have some physical activities so that you get energized and you are ready to take up any challenge. So my children are good enough to think wise and enact. Okay. So with this, we are going to get into the continuation of the chapter coordination compounds, where today we are going to learn about bonding in coordination compounds. Bonding. We know coordination compounds are formed with a metal atom or ion, and also we have some ligands. It can be a negative ligand, it can be a neutral ligand. We have a coordination sphere. We have some counter ions which are ionizable, which is responsible for the primary valency, and the secondary valencies which give the coordination number. This is what we know about coordination compound. Now, how do these ligands get bonded with the metal atom? That is what we are going to study in bonding of coordination compounds. Why only very few elements are capable or has got a property to form coordination compounds? Why the bonds show directional property, or why do they have magnetic or optical property? These are some of the questions that arises because we know transition metals are colored compounds, and why do they show characteristics colors? With this, we have some 4 theories which are important, that is valence bond theory, crystal field theory, ligand field theory and molecular orbital theory. But as of for this year, our syllabus is concerned, we are going to focus only on valence bond theory and crystal field theory. So these 2 theories are fair enough for us to understand the bonding in coordination compounds. If you see VBT, valence bond theory. So from the name it is very clear that the outermost electrons, the valence electrons, are wholly responsible for the bond formation. So when I write the subshell electronic configuration of any transition metal, I know for D block elements it is N-1 D, Ns, then comes Np, then comes Nd. But here when we are doing this valence bond theory, depending on the oxidation state, I repeat, depending on the oxidation state of the transition metal, we have 2 type of hybridization possible, 2 type of bonding possible. One is the low spin or inner orbital hybridization. The other one is a high spin or outer orbital hybridization. What does it mean? When I say inner orbital, N-1, that is here especially we have 3D, 4s, 4p, 4d taking part in the hybridization. Children, listen very carefully. We have 3D, 4s, 4p and 4d taking part in the bonding formation. So at that time when I say n minus 1d, that is 4 minus 1 is 3d, 3d, 4s, 4p. When those three orbitals take place in the hybridization, we call them as inner orbital, because the orbital which is inside is taking part in the bond formation. So, you call it as inner orbital or low spin hybridization. When 4s, 4p, 4d, that is when the outer orbital take part in the hybridization, you call it as high spin or outer orbital hybridization. So, these are the basic classification. With this, we are going to learn what is VBT and how does it designs or help us to find out the geometry of the complex. There are two ways of doing this VBT. One, once we know the geometry of the complex, we can decide the hybridization, or we can find out the magnetic behavior. Or once the magnetic behavior is known, we can find out the hybridization, and with that we will learn the geometry of the compound. So, these two methods, once geometry is known, you find out the magnetic behavior. The other one, the magnetic character is given, you will design the geometry of the compound. So, let us work out 2-3 examples to learn more about VBT. We shall learn about writing the valence bond theory using inner orbital and outer orbital complex. Now, how do we do it? Let us take an example where Hexa, Amine, Cobalt 3 complex is there, where the oxidation state of Cobalt is +3, and we know atomic number of Cobalt is 27. So, the outermost configuration is 3d7 4s2. So, once it becomes CO3 plus, Cobalt 3 plus, it loses 3 electrons. After losing the 3 electrons, we know the 2 electrons are lost from the outermost 4s subshell and 1 electron from 3d. So, the configuration that we get is 3d6, and given the complex forms an octahedral geometry with a diamagnetic character. So, we know when it is diamagnetic, there are no unpaired electrons, that is all the orbitals are completely filled. So, what happens here? I have to fill my 3d subshell with 6 electrons. So, as per the Hund's rule, how do we do? 1, 2, 3, 4, 5, and the 6 electrons, the pairing will start. Now, the most important, since it is given the complex forms a diamagnetic character, so we know there should be no unpaired electrons. So, what happens here? These electrons get shifted to the previous orbitals. There is a movement of the electrons within the orbitals. So, hence you get a structure like this, where the pairing has already been done because of the diamagnetic nature of the complex. So, now the hybridization starts. So, now we are left with 3d 2 orbitals, 4s 1 orbital and 4p 3 orbitals. And now we know there are 6 ammonia molecules which has to donate a pair of electrons with cobalt, the central metal atom, to form an octahedral geometry. So, how does this work? Now, let us see. Once these 3 are filled, so we have 6 electrons in 3d here. Now, these d2 comes here, and we have one s and 3 p orbitals. So, now here all this ammonia will be giving a pair of electrons to the central metal atom and forms a D2 Sp3 hybridization. Since the inner orbital is taking part in the hybridization, it forms a low spin complex, or we also call it as a inner orbital hybridization. Such type of hybridization, D2 Sp3, forms an octahedral geometry, as there are 6 ligands. These are neutral ligands, 6 ligands which forms a bond with a central metal atom, that is cobalt. So, this is an example where the inner orbital takes part in the hybridization. Now, if you consider the next example, the same cobalt but forming a bond with fluorine atoms. We have cobalt, hexa, fluoro, cobalt, 3. where the oxidation state of cobalt is again 3 plus. So cobalt, after losing the 3 electrons, becomes 3d6. But there is a change here. In the first question, it was given this complex is diamagnetic. So when it is diamagnetic, we know there are no unpaired electrons, all the electrons are paired. So what happens here? The magnetic character is known, we design the geometry and the nature of hybridization. And in the second question, they have given that this complex forms a paramagnetic behavior. It has a paramagnetic character. So what happens? Let me fill the 6 electrons in the 3D subshell. Since it is paramagnetic, I know there should be no pairing taking place. All these unpaired electrons should remain as such in the orbitals. There are no movement of electrons within the orbitals to make it paired so that it becomes diamagnetic. It is very clearly given to us in the question that this complex forms a paramagnetic character. So when it is paramagnetic, there are no pairing takes place. So we leave the 3D subshell as such. Now when it is left as such, we know 6 fluorine atoms has to be coordinated with the central metal atom. So what happens here? Here it remains like this, but this 4s, 4p and 4d will take part in the hybridization. So here what happens? This will remain as such sp3 and from 4d D2, 2 d orbitals will come and join with sp3. So it becomes sp3d2. So the hybridization is sp3d2 where the 4d subshell is taking part in the hybridization. So you call it as high spin or outer orbital complex. The geometry is again octahedral because we have 6 ligands, negative ligands, 6 fluorine atoms which is getting bonded with the central metal atom cobalt. The only difference between these two structures are diamagnetic, so pairing takes place, paramagnetic, so presence of unpaired electrons are essential. The geometry is both octahedral, but here it is D2 sp3, but here it is sp3 d2. Low spin, high spin, inner orbital, outer orbital complex. So in exam, you will be facing such questions where the geometry or the character is given, you will find the hybridization, or they may give you the nature of hybridization, because we know if D2 sp3 is given, what should be the magnetic character, whether the pairing should take place or it should be unpaired. So such questions arises when you solve the questions, right? So with this, the octahedral geometry is over. Now we will get into tetrahedral and square planar geometry. The coordination number 4. The last we were seeing about coordination number 6, that is octahedral geometry. Both showing octahedral, but one with D2 sp3, the other one with sp3 d2. So in this case, when the coordination number is 4, you have two type of hybridization possible. First one is sp3 forming a tetrahedral geometry. Second one is dsp2 which gives a square planar structure. So both are coordination number 4. But when you have sp3 hybridization, that gives a tetrahedral geometry. When you have dsp2, that shows a square planar structure. Now how to go about this? Again, the magnetic character decides the geometry of this complex. Tetrachloronickel 2 complex. In this, we know nickel atomic number 28 having 3d8 4s2. The oxidation state of nickel in this complex becomes +2, where 2 electrons are lost, which is lost from the 4s subshell. So it becomes 3d8. Now what am I supposed to do? With nickel 2 complex, I start filling the 8 electrons. So 5, 6, 7, 8. So I have 2 orbitals left with 2 unpaired electrons. But the question they have given very clearly that this particular complex shows a paramagnetic nature. Being paramagnetic, we are not supposed to make the pairing of the electrons, as presence of unpaired electrons makes this complex paramagnetic. So what am I supposed to do? These 2 electrons stay as such. There is no movement of these two electrons, but now I have 4 chlorine atoms which are sharing a pair of electrons with nickel. So here I make this as such. Now I need 4 orbitals to take part in the hybridization, where I take 4s and 4p. So 1 4s and 3 4p orbitals forms an Sp3 hybridization, where the chlorine atoms are donating a pair of electrons to these nickel central metal atom, forming an Sp3 hybridization with a tetrahedral geometry. Now let us get back into the case where we have the same coordination number 4, tetracyano nickel 2 complex, nickel having a +2 oxidation state, 2 electrons lost from the 4s subshell. So I have 3d8. So if I have to fill the electrons, I start filling using the Hund's rule. Now the question, they say this particular complex shows a diamagnetic nature. So when it is diamagnetic, I should make sure that there are no unpaired electrons. So what happens here? The electron from the last orbital gets shifted to the inner orbital. So I have a structure like this, where I have 4 orbitals where all the electrons are paired, 1 with no electrons. Now what is the next step? After having 4 electrons paired in 4 orbitals, so here I need to occupy my 4 cyanide ligand to the central metal atom nickel. So from the 3d, 1d orbital, 1 4s orbital and 2 4p orbital take part in the hybridization, where the cyanide ligand donates 4 pair of electrons to the central metal atom nickel, forming a dsp2 hybridization, which is a square planar geometry. What is the structure here? It is square planar. And what is the structure here? It is tetrahedral. So this is how the structures have been formed for both Sp3 and dsp2 structures. So this is the basic things that we need to know in valence bond theory. So valence bond theory helps us to determine the geometry of the complex, also the magnetic character. Children, just imagine if you have been given in the question that this particular complex forms a Sp3 hybridization. So we know after writing the first step, only S and P3 are taking part in the hybridization. Definitely we will not do the pairing. Am I right? We don't do the pairing of electrons. So when the pairing is not done, the structure must be paramagnetic, because it shows that there are the presence of unpaired electrons. Now in the other hand, when it is given in the question that this particular structure forms a square planar geometry, or it forms a dsp2 hybridization, find out the magnetic character. So definitely after filling the 8 electrons, we know there is one d subshell which is taking part in the hybridization. So in such case, definitely one d orbital must be available. So the 2 unpaired electrons becomes a paired one. So one electron gets shifted from the outer d orbital, that is the last d orbital, to the inner d orbital, thereby making the complex diamagnetic. So that's how the dsp2 hybridization is formed, or I would say it forms a square planar structure with a diamagnetic character. So I hope you are able to understand how VBT is helping us to find the geometry and the magnetic character. You have been given magnetic properties of coordination compounds. Just go through this paragraph, children, because it is not as important in the case for our board exam. Okay. Now when you come to limitations of valence bond theory, it involves a number of assumptions. Now how can I say so sure that it forms a paramagnetic character? Do we have an evidence? Have we done any experiment that shows that this complex shows a paramagnetic character? So it has all been assumed that this particular complex can be paramagnetic. That's why it is showing an Sp3 hybridization. It does not give quantitative interpretation of magnetic data. Yes, we are not very sure that definitely this complex must be diamagnetic. or this complex must be paramagnetic. It is not giving a proper evidence. It does not explain the color exhibited by the coordination compounds. Now, why do I say that this coordination compounds are colored compounds? What are the reasons behind that? The first particular reason is because of the presence of central metal atom. What is the role of a central metal atom here? It gets bonded with the neutral ligands or the negative ligands, and we already know that D block elements, that is the transition elements, show colored compounds because they have a property of accepting or they transmitting a light when it been passed through it. But this particular valence bond theory does not explain about the color of the compound. It does not give quantitative interpretation of thermodynamic stability. What is meant by stability? How do I say a compound is stable or not? When it does not react, right? The reactivity of this particular complex shows the stability. But here this theory does not explain the stability of this complex. It does not make exact prediction regarding tetrahedral and square planar structure. It's all been our assumptions. This is all theory which is being designed, which we are learning. There is no particular prediction or there is no particular proper theory which is being giving us an exact data that this particular complex will have sp3. So, for coordination number 4, when I say coordination 6, though the complex may be inner orbital or outer orbital, both having D2 sp3 and sp3 D2, in this case having a coordination number 4, both can show both tetrahedral and square planar. How a coordination number 4 can show two different type of complex? Does it possible? Is that possible when we do it in a practical wise? It does not distinguish between a weak and a strong ligand. What does it mean? We are going to get into the next particular theory which is helping us to understand more about ligands, because ligands play a major role when a coordination compounds are formed. Any type of hybridization that we learn here, it is just because of the ligands that are getting bonded to the central metal atom. Otherwise, central metal atom does not have any particular role. It is just getting bonded to the ligands. Ligands has got two type of character. One having a strong force towards, attractive force towards the central metal atom, or a very weak force towards the central metal atom. So, these differences, that is a strong or a weaker ligand, cannot be explained by the valence bond theory, which is further being explained or given a very clear explanation by the crystal field theory, which we will be learning in the next class. So, crystal field theory and how it helps us to find out the complex and how it helps us to find out the nature of the ligand, the nature of the bond it forms with the central metal atom. Each and every single tiny information we will be learning using the crystal field theory. So, till this I want you all to go through with various examples that are given in the textbook. Make sure that you do it, and if you have any doubt, don't hesitate to call the teacher. Okay. Take care children. All the best for your exams. Do well. Bye.
Valence bond theory. Bonding in coordination compounds. The scientist Alfred Werner was the first person to propose the theory of bond formation in coordination complexes. However, Werner's theory could not explain why only certain elements formed coordination compounds, why the bonds in the coordination complexes have directional nature, why certain complexes have a magnetic nature. The limitations of Werner's theory were overcome by few modern theories. Of these, one was the valence bond theory. Let's learn about the bonding in coordination compounds with the help of the valence bond theory. An orbital is a region of space around the nucleus of an atom, where the probability of finding electrons is maximum. 4 orbitals have been defined for an atom, namely S, P, D and F. The atomic orbitals of a metal intermix with each other to give the same number of identical and equal energy orbitals. For example, an s orbital and a p orbital intermix to give a hybrid sp orbital. Different types of hybrid orbitals are formed by the intermixing of different combinations of atomic orbitals. These new orbitals are referred to as hybrid orbitals. In complex compounds, all the bonds between the metal and ligands are identical due to the formation of hybrid orbitals. The empty hybrid orbital of the central metal atom overlaps with the filled orbitals of the ligands containing a lone pair of electrons by hybridization. The type of hybridization and coordination number in the complex determines its geometry. Look at the table on the screen to understand the geometry of the complex compounds based on the type of hybridization and the coordination number. Let us now understand the common types of hybridizations which occur in the coordination complexes. Click each tab to learn more. Let's learn about DsP2 hybridization by taking the example of nickel tetracyanide 2 complex ion. In the nickel tetracyanide complex, there are 4 ligands, each with a lone pair of electrons. Hence, in order to form a bond, these ligands require 4 vacant hybrid orbitals in the central metal atom, nickel. The electronic configuration of nickel is 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d8. The valence and penultimate shell electronic configuration of nickel is 3d8 and 4s2. In nickel tetracyanide 2 complex, nickel ion has +2 oxidation state. Therefore, the valence electronic configuration of nickel ion is 3d8. Under the influence of the ligands, the unpaired electrons present in the 3d orbital become paired, thereby resulting in a vacant d orbital. Nickel ion has 1 vacant orbital and requires 3 more vacant orbitals to accept the 4 lone pairs of electrons present in the ligands. These 3 orbitals are obtained from 4s and 4p orbitals. Hence, the 3d, 4s and 4p vacant orbitals of nickel ion form 4 dsp2 hybrid orbitals. These are occupied by the 4 lone pair of electrons of the cyanide ligands, thereby resulting in dsp2 hybridized nickel cyanide bond by dsp2 hybridization. There are no unpaired electrons in this complex. Such complexes are diamagnetic in nature. Complexes with unpaired electrons are paramagnetic in nature. The complex with dsp2 hybridization has square planar geometry. Thus, nickel tetracyanide 2 complex ion has square planar geometry. Let's learn about sp3 hybridization by taking the example of Tetracarbonyl nickel 0 complex. In the Tetracarbonyl nickel complex, there are 4 carbonyl ligands, each with a lone pair of electrons. Hence, in order to form a bond, these ligands require 4 vacant hybrid orbitals in the central metal atom, nickel. The electronic configuration of nickel is 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d8. Valence and penultimate shell electronic configuration of nickel is 3d8 and 4s2. Under the influence of the ligands, the unpaired electrons present in the 3d orbital become paired electrons, thereby resulting in a vacant d orbital. Owing to the lower energy level of the 3d orbital as compared to the 4s orbital, a pair of electrons from the 4s orbital moves into the vacant d orbital. Therefore, the valence electronic configuration of nickel ion is 3d10. Nickel requires 4 vacant orbitals to accept the lone pairs of electrons from the carbonyl ligands. These 4 orbitals are obtained from 4s and 4p energy levels. 4s and 4p vacant orbitals of nickel form 4 sp3 hybrid orbitals. The hybrid orbitals are occupied by the 4 lone pairs of electrons of carbonyl ligands, thereby resulting in sp3 hybridized nickel-carbonyl bond by sp3 hybridization. The complex is diamagnetic in nature as there are no unpaired electrons. The complex with sp3 hybridization has tetrahedral geometry. Thus, tetracarbonyl nickel complex has tetrahedral geometry. Let's learn about D2sp3 hybridization by taking the example of Hexa-Amine Cobalt 3 complex ion. In the Hexa-Amine Cobalt complex, there are 6 ligands, each with a lone pair of electrons. Hence, in order to form a bond with the metals, these ligands require 6 vacant hybrid orbitals of the central metal cobalt. The electronic configuration of cobalt is 1s2, 2s2, 2p6, 3s2, 3p6, 3d7, 4s2. Valence and penultimate shell electronic configuration of cobalt is 3d7 and 4s2. In the Hexa-Amine Cobalt complex, cobalt has +3 oxidation state. Therefore, the valence electronic configuration of cobalt ion is 3d6. Under the influence of ligands, the unpaired electrons pair themselves, thereby resulting in 2 vacant d orbitals. Cobalt has 2 vacant orbitals and requires 4 vacant orbitals to accept the lone pairs of electrons from the 6 ammonia ligands. These 4 orbitals are obtained from 4s and 4p orbitals. Hence, the 3d, 4s and 4p vacant orbitals of cobalt ion form 6 D2sp3 hybrid orbitals. These are occupied by the 6 lone pairs of electrons of ammonia ligands, thereby resulting in D2sp3 hybridized cobalt-ammonia bond by D2sp3 hybridization. The complex is diamagnetic in nature as there are no unpaired electrons. The complex with D2sp3 hybridization has octahedral geometry. Let's learn about dsp3 hybridization by taking the example of pentacarbonyl ion 0 complex. In the pentacarbonyl ion 0 complex, there are 5 carbonyl ligands, each with a lone pair of electrons. Hence, in order to form a bond, these ligands require 5 vacant hybrid orbitals in the central metal atom, iron. The electronic configuration of iron is 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d6. Valence and penultimate shell electronic configuration of iron is 3d6 and 4s2. Under the influence of the ligands, the unpaired electrons present in the 3d orbital become paired electrons, thereby resulting in vacant d orbitals. Because of the lower energy level of the 3d orbital as compared to the 4s orbital, the pair of electrons from the 4s orbital moves into the vacant d orbital. Therefore, the valence electronic configuration of iron is 3d8. Iron with one vacant d orbital requires 4 more vacant orbitals to accept the 5 lone pairs of electrons from the carbonyl ligands. These 4 orbitals are obtained from 4s and 4p energy levels. 3d, 4s and 4p vacant orbitals of iron form 5d sp3 hybrid orbitals. The hybrid orbitals are occupied by the 5 lone pairs of electrons of carbonyl ligands, thereby resulting in dsp3 hybridized ferrous carbonyl bond by dsp3 hybridization. The complex with dsp3 hybridization has trigonal bipyramidal geometry. Thus, pentacarbonyl iron complex has trigonal bipyramidal geometry. Let's quickly recapitulate the bonding in complex coordination compounds.